So now I want to get back to what I was talking about last time, which is lower bounds and how you prove lower bounds. And there are two major styles of proof for proving lower bounds. Lower bounds, now we're talking about lower bounds on a problem or lower bounds on a class of algorithms, not a specific algorithm per se, although we then apply that general theorem about classes of algorithms to specific algorithms. There are two styles that we'll talk about. One is called information theory lower bounds, which I started last time. And then today we'll also talk about adversary lower bounds. So the basic idea for information theory lower bounds, let me review. Is that you're thinking of a class of algorithms which branch. Each algorithm in that class has the structure that it does some straight line code, however complicated that may be. Then it branches. And last time we said it was going to branch just in two ways, but actually any finite branching here will do, as long as there's a bound on the number of ways it can branch, independent of the size of the problem instance. But we'll just look at it as two. And then depending on if it branched this way, it does some particular straight line code. Maybe it branches again, does some straight line code, which may or may not be the same, but usually considered different. And it goes like this until finally each one of these execution paths, this represents a path from the start down to a leaf, represents some possible execution of that algorithm. And down at the leaves, we do the algorithm puts out some answer. So we're looking at classes of algorithms that can be described in this way. And then we wanted to develop, from this viewpoint, a lower bound on the worst case number of operations, actually the worst case number of branches that some path in this execution tree must take. Okay? So we ask the following question. First question. Well, if there are, I'm making this a little more general. If there are k possible results or outputs, all right, then the tree here must have at least k leaves. Actually, so this isn't a question. This was the answer to something I phrased as a question. Okay, so this is really a simple-minded claim. It has to have as many leaves in this picture as there are possible outputs that the algorithm is supposed to give. Because if there was one output that wasn't represented at one of these leaves, then the algorithm could never give that. And if you therefore gave the data to the algorithm that was supposed to give that output, you would see that the algorithm was defective. So this is a rather simple-minded claim. Okay, and any particular diagram like this is for a fixed input size, which we're usually using n to denote. So for every n, for any algorithm in this class and for any n, there's one of these actual tangible diagrams. You take your favorite sorting algorithm and n equals 26, and you should be able to lay out, it's very tedious, but you should be able to lay out such a diagram. And in the undergraduate courses, we actually ask people to do that for some small cases. Very, very tedious, but you get the idea. So this is the first claim. If there are k possible results, then the tree must have at least k leaves. And the second claim is any tree, any binary tree with k leaves must have depth greater than or equal to log base 2 of k. Well, it's just a fact about binary trees. You're doubling at most the number of nodes at each level as you go down. So there has to be some path in here which has depth at least log base 2 of k, which means that the worst case behavior of that algorithm must be at least log base 2 of k. Now, that is, I can give some input to the algorithm that forces it where, let's say this is the deepest leaf. I give input for which this is the right output, and the algorithm will proceed down this path, and this path has length at least log base 2 of k. Now, we don't want to express the running times in terms of k. We want to express the running times in terms of n, the input size. So the next thing is to relate k and n, and that depends on the particular problem. Right? So this is quite general. And so to make this specific, to a problem P, remember P stood for a whole problem, let's say sorting as an example, you have to relate k to n. So in the case of sorting, what is k? N again was the size of the input. It's the size of the input list, let's say. So what was k? N factorial. So for sorting, well, actually k is the, must have at least k leaves. Yeah, k is equal to n factorial. Because they're n factorial different answers that a sorting algorithm must be able to provide. So that gives us the following theorem. Any sorting algorithm, and here's the key thing, of the right sort, must take omega of log base 2 n factorial operations in worst case. Yeah?
What do you mean by right sort?
Well, that's what I was going to ask you. I put that up to be sort of as a pun, but also, yeah. What do I mean of the right sort? Yeah?
Comparison based. I mean, you have to be able to face it. You have to be able to plug it into this tree.
Yeah. Okay, your first answer was comparison based, which shows that you've seen this movie before, because that's the canonical answer, and then you'll find that in our book, and it's the wrong answer. Again, it amazes me that these guys, CLR, at least L and R, are quite famous. It kind of amazes me that they screwed it up. It's not comparison-based necessarily. It's that you can fit it into this framework.
You have to make a decision somewhere.
You
have to make a decision.
No. It's like it's binary decision-based.
Binary, or I mumbled something about this, as long as we make this finite, some fixed bound. But it's got to fit into this framework. This framework has straight line code, then branching, where the branching is bounded by a finite number that's independent of n. And as long as your algorithm fits in that framework, there's got to be a path here which has length, log base 2, of the number of leaves. And if we're talking about sorting, the number of leaves is at least n factorial. So that's what I mean by of the right sort. It fits into that framework. If I took this out, then I'd be talking about things that's so broad that I can't even get my hands. I can't conceive really of all the possible algorithms there are for sorting. Who knows what kind of crazy thing somebody's going to come up with in the future. But if their algorithm fits into this framework, that then we have a theorem, this theorem, which provides a lower bound on how many operations that algorithm must do in worst case. Okay? Does everybody get this? And log base 2 of n factorial, we mentioned last time, and you can look in the book, is about n log n. It's not too hard to establish this. I mean, if you just go back to Stirling's formula for factorial, this is immediate. And there are even easier ways of seeing this relationship. You don't have to go back to Stirling. Okay, so this is the famous n log n lower bound on sorting that everybody quotes. And I used to think that as a definition of a computer scientist, I mean, you have to be able to wake up in the middle of the night and say n log n as the first things out of your mouth. This lower bound is what makes this a community. One of the things that makes sort of, you can be sure that everybody who's gone through computer science education has seen this result in one form or another. And it's in our book on page 172. But there it's called the decision tree method or decision tree argument, and it is proven just in the case of sorting algorithms. It wasn't given in this generality. And we'll get to next why I think they really screwed it up. Okay, any questions about this? Can anybody provide an intuition why this is called information theory? Yeah.
Could you motivate a kind of sorting algorithm that's not of the right sort without giving a specific one?
No, I don't know any.
Okay.
Yeah.
Anything current, not
Sorry, say it again?
anything not because you're now.
Oh, I don't know. You're getting beyond my. You're talking about parallel programming of some sort. You'd have to really look at the details of that to see whether or not that's going to fit into that framework. If you have a finite number of processors that's fixed, then the answer is almost surely yes, it's going to fit in there. It doesn't matter how much you do in parallel. But if you go to a model where you can really just keep throwing resources at the problem, no matter, as the size of the problem grows, then you're probably going to get outside that model. Okay? So these kind of models are critically important. But the question was, can I propose an algorithm that's outside of this model? And I can't. The book does, and that's what we're going to get to next. Okay, and that's why I think they really kind of screwed it up. So did you have a question? Or?
Is that the entropy of the
Okay, so I actually had mumbled a question, which was, why is this thing called information theory lower bound? And people who know some information theory, and I know almost none, might have some intuition about that, but I don't know what the right answer is. Except that, I mean, my limited understanding of information theory has to do with how many bits it takes to code some set of objects. And what are we coding here, really? What are the objects? The objects that are being coded are the different behaviors of the algorithm. This is a set of behaviors, n factorial of them. And each one is being coded by a path, a sequential path down this algorithm. Okay? And you know that you need log base 2 of the size of the set that's being encoded, that many bits, to encode that set. And so that, in kind of a hand-waving way, is my understanding of why this is called information theory. But if you start talking about things like entropy or information, you might have better intuition about it, but then you're really beyond what I know for these things. So this is the information theory argument. And we're going to get to other arguments, adversary arguments, later. Now, the next thing the book does, it's actually kind of funny. They give this argument in page 172 in a chapter that's called Linear Time Sorting Methods, or something like that. So already the chapter heading is telling you to be suspicious of this, because this is not linear. This is n log n. This grows bigger than linear. Okay? So why they put that there, I'm not sure, but they start out the chapter by telling you you need n log n operations to sort. And then they go on to show you some other methods. So let me just pick one of those. They talk about a few. The one that I'll talk about is what they call counting. I think they call it counting sorting. So in this problem, you have n numbers, let's say in an array, 1 through n. These are unsorted. And actually, integers. Actually, positive integers. Okay? And you want to create an array where those integers are in sorted order. Let's say smallest to largest. And you'll also have available to you some contiguous location in memory that's denoted 1 through k. This k, by the way, is not related to that k. Okay, so this is just some number where we know that k is greater than or equal to n. At first, we're going to tighten that up in a while, but initially, that's just greater than or equal to n. So how does this algorithm proceed? Basically, step 1 is you scan A. So you're just going to go through the elements of A. And I'll do... I'm trying to make this a sort of a mixture of English and Fortran or something. Scan A and increment C of A. Well, I guess I do need this. So this scan is, I equals 1 through n. When cell I of A is scanned. And this is such a simple idea. It's just getting munged by this pseudocode. Let me just give you a simple example first. Yeah.
Don't we need to know the range of the numbers in A to do this?
No.
But then how do we know how big to make C?
Oh.
Max of A. Max of A.
Okay, let's do that. That's the simplest thing to do. Yeah, and probably maybe they do that as well. Okay, so positive integers, let's say less than or equal to, I think k will do it. Okay. So yeah, let's do that. I don't know how they do that in the book or not, but this will illustrate the point I'm going to get to anyway. So yeah, the numbers are in a range, positive integers, so they're between 1 and k. All right. Yeah, and you can see, thank you, already you can see that this would be an out of bounds if I didn't do that. All right, so let's just take some example here. 2, 5, 1, 4, 3, 7, 2, 8. Okay? And so k, let's say, is equal to 10. It's some number which is greater than or equal to n, and it's greater than, and the largest number here is less than or equal to k. All right. So all we're doing in C, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All I want to do in C, all I want to do with this scan is to count the number of these distinct elements there are in A. That's really all I'm trying to do. I see a 2, so this becomes a 1 here. I see a 5, well, that becomes a 1. I see a 1, that becomes a 1. I see a 4, that becomes a... I see a 3, actually not... I see a 7. I see another 2. So finally something actually gets changed there. I see an 8. and I'm done. Okay? And let's say I had initialized these as zeros. So it's a very simple-minded thing. I'm just scanning through A, and every time I see a particular value in here, I use that as an address and increment the count that's there. All right? Next step, step 2, scan C and compute running totals. All right, so C gets scanned, and this becomes 1, 3, 4, 5, 6, 6, 7, 8, 9, 8, 8. Okay? So I'm just keeping the running total left to right. 1 plus 2 is 3, plus 1 is 4, plus 1, etc. Okay? Now you should be able to see how to create B from C. Okay, we want to use C to create B. Well, if I now scan C, I scan this at this point, what I see is that there's one element in the original input that has value 1. Okay? So I put it at the head of the list. Then I see, oh, this is a bigger number than this one is. So there must be some elements in the list which have value 2. And how many are there? 2 of them. It's 3 minus 1. Okay? 2 and 2. Oh, this one is bigger than 3, so that's by 1. And so there must be one element of 3. Same reasoning here. There must be one of 4. Here there must be one of 5. Now this number is the same. This number is the same, so there's none of 6. So I'm not going to write down a 6. Okay? Then I see this is bigger, so there's 1 of 7. And this is bigger, so there's 1 of 8. And then these are all the same, so there's nothing bigger than that. Okay? Everybody understand how a scan here, a scan of the running total of C tells me how to build B? Question?
Why do I even need the running totals? Because I'm using it to just get back the numbers that were in C before.
The numbers that are in C?
Well, you look at the 1 and the 3 and you say their difference is 2. Well, that's already in C.
No, but all of them aren't in C.
Where's the number 2 in C, though?
That 2 is 2.
This is C at the moment. We're looking at it.
Oh.
Yeah.
The problem is we don't even have to calculate this running total. I think it's just to confuse the reader. As soon as we have the entries in C, we see that there's 1 mark in the area for 1. We just output 1, 1. And then we have 2 marks in the area for 2, so we output 2 2s, and we're done. We don't even have to calculate this running total.
Oh, okay. This tells you where to address. Okay. From doing this, you can figure out the specific address. If I look in the middle here, and I want to know where's element 7 to go in the list, then just by looking at these two, I can figure that out. But I think, okay, so fine, you're right. If I just were to do this sequentially, yes, this looks like a little overkill. But whether it's silly programming or not, everybody should be able to see that this is a way in which we can end up with a sorted list here, and this is of size n. The sorted list here by using this C device of counting. That's why they call it counting. Otherwise, I might give it a different name. By using this kind of counting device to represent how many times you've seen a particular number in your input list A. All right. Any question about correctness? Does this work? Provided that K is big enough, okay, bigger than the largest integer in your input, this should work. In fact, K could be huge. All right. We could have a lot of space in here, and a lot of these things would be zeros if K is much, much bigger than n, which is possible. So what is the running time of this method? What can we say about the running time of this method? Yeah.
Well, it's either O of n or O of k, whatever is larger. K is larger, is O of k.
Yes. At this point, it's O of k. All right? We had to, it was an implicit, I didn't mention explicitly that we were going to initialize this, but if we did, that would be order k operations already. But anyway, a scan of C, whether you scan this version of C or this version of C, that's an operation which takes something proportional to k operations. That's a task that takes something proportional to k operations. So this method well, maybe I should, before I ask what its running time is, what's the primitive operation? Or what are the primitive operations? What are the fundamental things that this algorithm is doing?
Array lookup.
Okay, array lookup, which means really it's taking an integer as an address. It sees a number in array A, and it uses that as an address, as an index into C. So that's certainly a primitive operation. And then the other ones are reading and writing. Which seems innocuous enough. But this is different. We've never seen this operation before. Okay? Now, getting back to what I was just saying, the running time is big O of k. Does that violate our n log n bound? Not yet. It's just different. Okay? You've got a running time which is bounded by a parameter, in this case k, which never appeared previously. But why this is considered linear time is if k itself is big O of n, then the running time is order n. And then this method is declared linear. Its running time is proportional to the size of the input. N was the size of the input. Okay? Now, does that violate this? Well, it seems to contradict it anyway. This is bigger. This is remember, this is an omega. This is supposed to grow as fast, at least as fast as n log n. And here you have something which is growing no faster than n. Yeah?
That's not considering all possible inputs. Not in this framework.
Well, I never said anything about the range of inputs when I developed this lower bound argument.
I can also say that bubble sort is linear time when there are special case of inputs, one swipe over and done. That's clearly not so.
Everything you're saying is true. The question is, does it go to the heart of this seeming contradiction? And if you go back to the generality of this lower bound argument, I never said anything about the range of input, except implicitly that there were n factorial different outputs. When you restrict your numbers to be between 1 and n, there's still n factorial different outputs. Okay? The output, remember, is telling you a relationship between the order of the elements as they were given, the unsorted, in their positions, to the final sorted order. It's giving you a permutation which takes the input locations to the output position in the list. So even though the numbers are restricted to between 1 and n, or 1 and 5n, or 20n, they're still n factorial different behaviors. So it seems to me at first that this framework should still apply, that this specific counting algorithm, until we see why it doesn't fit in here, we got a problem. And it's not the fact that this is a restricted domain of input.
So it's not decision-based?
It's what?
It's not decision-based like that approach?
Not decision-based. Well, but you see, it does branch. That program branches. It reads a number, and then it does something in array C based on what it saw. That's a branch. Yeah?
Branching operator based on only one element in the given?
It's the number of choices that the branch can go to.
Yeah, okay, well, we'll forget we heard that for a moment. Let's hear some more. Now, the suggestion in the back was that this is not this operation is not a binary operation. It's just looking at one number and then deciding what to do. You're not looking at two. But I didn't say anything about what was causing this branch. I just said it was branching. That's why I wanted to give this in complete generality instead of saying what's going on here is a comparison between two numbers. Because what the book does to explain this anomaly, to explain this seeming contradiction, it gave this proof first where at the branch, this was a comparison between two numbers. And it developed this theorem in that framework. And then it shows you this algorithm over here and says, what's the resolution? And then it says, well, the resolution is that this algorithm over here isn't comparing two numbers at a time. And I hope most of you see that that's nonsense. That's not at the heart of the matter at all. So this algorithm is superficially different than an algorithm that compares two numbers at a time, but that's really irrelevant. This algorithm branches. It does some work. It does, on the basis of that work, it branches. And it does some additional work. And on the basis of what it does, it branches again.
How does it branch? A branch you have a lot of branches like log k, log base k to the end of k is very big.
Now you're speaking of this k, yeah. Unfortunately, okay, so let me give you, yeah, we could develop that viewpoint too probably, but let me give you the answer that Eric suggested, was when you map this algorithm into a branching structure, it's branching n ways. It's branching k ways, this k, okay? It sees a number and decides what to do with it. That's a k-way branch. All right? And that k is not finite. That k grows, has to grow with n. The number of integers. Say it again?
It depends on you.
As I make the problem instances bigger and bigger, okay, well, I can give you instance, I mean, as I allow the problem instance to get bigger, we can give it data where all the numbers are distinct. And therefore, as the problem instances get bigger, k has to be bigger, otherwise the algorithm won't work. Okay? And when this algorithm is looking at a single number and then incrementing a location in array C, that's a k-way branch. If you lay it out here, the action that's happening, so here we're looking at a number. Look at AI and do something. Well, what something are you doing? That's the straight line code where you're incrementing some location in C. It's a different location in C depending on what you see here. And so that is a k-way. Now, I'm going to write it this way. It's got to be at least n-way branch. All right?
So it still fit into that one because the log n vector becomes 1, approximately 1. So it's fit in
Well, so what happens is this becomes a log n of n factorial. And what is log n of n factorial? It's what? It's about n. Some of the logs. Well, it's about n. I'll let you do the math at home. So there's no contradiction. I mean, this framework works. This framework does give us a lower bound. It's not a very interesting one, but it gives us a lower bound on how many operations such an algorithm must take. It just says it's got to be at least n. And in fact, this algorithm, among its primitive operations, does at most n, primitive or k, primitive operations. And actually, this is log k. So there's no contradiction here at all. It's just that that algorithm, the counting algorithm, doesn't fit into the framework that I first set up, where I insisted that the branching factor be finite. This allows you implicitly a branching factor which grows with the size of the input, or which can grow with the size of the input. Then you have to determine yourself whether you think that's a realistic, which of these two models is more realistic and more allowable. That you insist on a finite k, or you allow k to increase, the branching factor to increase as the size of the problem increases. Okay? All right. So we got into some finer points than we would do at the undergraduate level, and that's why this is a grad course.
So that's why it should be the AI less than so not K greater than, it should be AI less than.
Yeah. I'm sorry, where's the contradiction?
Means Y equal N greater than K should be AI less than K.
Well, AI less than k is essentially implied here. The set of integers, they're positive unsorted integers less than or equal to k. And I can form data where all the numbers are distinct, and therefore k has got to be greater than or equal to n. Okay? Yeah?
It almost doesn't make sense, because from what you've written there, it would seem that the bound is lower if k is greater. Does that make sense?
The bound, well, yes, that's true. This lower bound can be smaller as k gets bigger. You're branching in more ways, so the depth of the tree is going to be smaller.
So if your numbers can take larger values, you can be done quicker. Does that make sense?
No. First thing, let me point out, there's nothing wrong with proving an uninteresting lower bound. And that happens all the time. Okay, so if you're pointing out that under certain circumstances this lower bound is way below what you think a typical algorithm would do, there's no contradiction there. It's just saying this is not a very powerful technique for those algorithms. This is not a very powerful lower bounding technique for those algorithms. So yeah, that's fine. Other question, comment? Okay, and in fact, information theory lower bounds are often uninteresting. But what I'm trying to point out here is that they're correct. When the book said, oh, this style of reasoning didn't work because I now have an algorithm that doesn't make comparisons between two numbers, that was really nonsense. The right way to view it is that this algorithm branches n ways or more, and therefore you have to incorporate that into this line of reasoning, which then gives you this, which tells you something which is not a contradiction. Yeah.
So for the regular sorting algorithms, the information theory lower bound gives us an interesting result, and for the k-way branching, it gives us a less interesting result.
Well, let me ask you: is the n log n interesting? The n log n lower bound interesting? It is, because we have an n log n upper bound. We have algorithms such as merge sort, which we showed their running time was big O of n log n. And it certainly fits into that framework. There's no n-way branching in that algorithm. And now we have a lower bound argument which says that for any algorithm that fits into that framework, it has to take omega of n log n comparisons in worst case. So we have an upper bound and a matching lower bound, an upper bound for a specific algorithm, a lower bound for a class of algorithms which that algorithm is in. They're essentially the same bound, and so that is interesting. You now know a lot about merge sort and you know not only what its worst case behavior is from both sides, but you also can declare it to be optimal because it's in a worst case sense, because you can't get an algorithm, at least in that class, whose worst case behavior is going to be below that n log n. Okay, so here is actually a sort of follow-up question to what we talked about 2 lectures ago. Here's the question. We know, we have established that the worst case running time of merge sort, a specific algorithm, is theta of n log n. True or false? Remember how I harangued two lectures ago on how we had not yet established this for merge sort? Have we now established it?
Didn't you just say we did?
It's cheating to listen to me. Yeah. Yeah. We had an upper bound that was specific for merge sort. We now have a lower bound, which is general for a class of algorithms that merge sort belongs to. And so, yes, true. We have established that. Okay. Just to show you how uninteresting information theory lower bounds can be, let's take the problem of the following problem. You're given an ordered list, and you're given another number, x. And you want to know, and let's just really simplify it, you're guaranteed that x is in the list. And you want to know where x is in that list. What do?
Binary search.
Binary search. Log n comparisons, log base 2n comparisons. Everybody knows how to do that. Okay. Now let's try to apply information theory to say that that's optimal. Okay. Ooh, sorry, this is going to work. I was trying to pick one that didn't work. Well, let's just do this anyway. Good illustration. All right. So we go back to the general framework, and you have to ask always. I apologize for the use of this k. It's different than the. Anyway. If there are k possible results, then the tree must have at least k leaves. So what is k in the case of this problem? N. So in this case, k, number of leaves is equal to n, actually greater than or equal if you want to be perfectly general. There are n possible answers as to where that element is. And so definitely you've got to have at least n leaves. If you had fewer than n leaves, there's some output that you could never have, and therefore the algorithm would be defective whenever you gave it input where that was the right answer. Okay? So if you have this tree and there are n leaves, what's the height of the tree at least? Is greater than or equal to log base 2 of n. And so what you see is that any algorithm that at least fits into this framework has to have some path in it which is length at least log base 2 of n. Well, that was the same upper bound. It was the number of comparisons that was done by binary search. And so you have an upper bound for binary search, and you have a matching lower bound for a class of algorithms, and you now know that binary search is optimal. So actually, that was interesting. Okay, now let me try to make this uninteresting. Let's take the problem. You're given an ordered list, and you're given the number x, and you want to know, is x in the list? And you don't care where it is. You just want to know, is it in the list? Okay? Then we'll try to do the same thing. We'll say, okay, we're interested in algorithms that have a branching structure, and when they get down to the leaves, the algorithm has to give an answer. How many possible answers are there? Two. Is it in the list? Yes. No. Okay? So now the size of the list of the leaf set is 2, and you apply the methodology which says there is a path of length greater than or equal to log base 2 of 2. What's log base 2 of 2? 1. This is a true statement. It's just uninteresting. Okay? And because it's a lower bound which is so far beneath any algorithm that we know of that can actually answer this question. Because actually, I don't know an algorithm that can answer this question without also finding out where x is, or that x is not there. I mean, I don't know an algorithm that can answer this question in better than log base 2n queries, and yet here's a lower bound which says only that it's got to at least do one query. You know, it's got to look at the input. And of course, you knew that anyway. All right. So information theory lower bounds sometimes give you a very quick way of matching upper bounds, and when they do, that's great. And in the sorting arena, that happens, and there are other places where this happens as well. But generally, well, there are many, many cases where they don't. So then you need a more powerful technique, and that's the adversary lower bound argument.